So let me start at the very beginning. Okay. So the setup is basically that of the positive mass theorem. We have an initial data set, and we'll be working in arbitrary dimensions. So the Riemannian metric is denoted by G, and K is the second fundamental form of the embedding in the space-time. And then with the Gauss-Kadazi equations, we have the constraint equations relating curvatures and the traces of the second fundamental form. So mu is the matter density, and J denotes the momentum density. And we'll always assume the dominant energy condition. So let's see if I can do a pointer here. So usually throughout the talk, blue will denote the dominant energy condition, which just says that all measured energy densities are non-negative. Okay. So another important assumption that we have is, of course, the fact that these are asymptotically flat. Okay, so we'll just deal with one end. And so outside some set, the manifold is diffeomorphic to Rn minus a ball. And there's some fall off to the Euclidean metric, and the second fundamental form should decay to 0. And one can put weaker decay here when you want to define the mass and the energy and linear momentum. But that's not important for us. We're just going to take the most simple form of the fall off, which gives you the rate of decay of the Green's function and one order of decay more for the second fundamental form. So these give us a well-defined ADM energy and linear momentum. You can just see that these integrals on arbitrarily large spheres converge and are finite due to the decay. And typically, one can deal with the linear momentum, but for us, it's not important. We'll just set it equal to 0 or just ignore it. In that case, we'll be referring to the energy as the mass because they agree in that situation. Okay. So for us, the parameter that we'll be interested in is little m, okay, the mass. So what does the positive mass theorem say? So this is the space-time version, so we restrict ourselves to dimensions between 3 and 7 due to singularities. Even though the Riemannian case has been proven in all dimensions, the space-time version, as far as I know, is only valid up to dimension 7 at this time because of the solution of the Zhang's equation, which mirrors that, the regularity theory mirrors that of minimal surfaces, so you have these possible codimension 7 singularities. So we can't, at this point, extend the proof as far as I know. So what it says is that under the conditions that we've laid out, you have an asymptotically flat initial data set, and you have the dominant energy condition holding. Then the mass is non-negative, and you see there's a little bit of an extra decay we put for the trace of the second fundamental form. Okay. That is so that we can solve the Zhang equation and make sure that there's appropriate barrier so that it doesn't contribute to the mass. So we'll discuss that throughout the talk. Okay, so there are different versions, different approaches. So if you make further assumptions like that the manifold is spin or that it's Kähler or has some extra symmetries, the space-time positive mass theorem can hold in all dimensions. But we will restrict to the the approach by Shen and Yao, and so then we'll have these dimensions unless we assume symmetry, which will be the topic of this talk. All right, so with the positive mass theorem, there's a rigidity statement. So what does the rigidity statement say? It says that if the mass is 0 under the assumptions of the previous theorem, that one gets an embedding, isometric embedding into Minkowski space, okay, via a graph. Okay, so the graph is this function little f, okay, and this just states that the induced metric on the graph is the one given by your initial data. But it's not just an isometric embedding. What it's saying is that the second fundamental forms agree. So H will denote the second fundamental form of the graph in Minkowski space, and we're saying that agrees with the second fundamental form of the given initial data. Okay, so it's a separate piece. Isometric embedding plus equality of second fundamental forms. Okay. Moreover, there is hidden in this description here implicitly a diffeomorphism between M and Euclidean space. Okay? So when I write this graph, X denotes a point in M. We're just identifying it with a point in Euclidean space. And so that's part of the theorem. So when mass is 0, you actually get your diffeomorphic to Euclidean space. Okay, so that's part of the theorem as well. So what would a rigidity? So what is the question that we are trying to investigate today? Today it says that if the mass is getting very small, should you get approximate embeddings into Minkowski, something of this nature? So either you're getting approximate embeddings or you're embedding to some spacetime that's getting close to Minkowski, something of this nature. That's what an appropriate rigidity question would be. What is happening to these initial data as you approach zero mass? Okay. So for some intuition, we go to a simpler setting of the time symmetric case, which has been studied previously by Lee and Sormani. So let's recall what the positive mass theorem says in this setting. It's a comparison theorem for manifolds of non-negative scalar curvature. So you have an asymptotically flat manifold, non-negative scalar curvature satisfying the dominant energy condition, which is just the same as non-negative scalar curvature. Then the mass is non-negative and the mass is 0. You are isometric to Euclidean space. So you embed in a Minkowski space as the t equals 0 slice. And so if the mass is getting close to 0, what can you expect to happen to the geometry of these manifolds? You expect them to be getting close to Euclidean space in some sense. So another motivation, that's a natural geometric question. You can ask rigidity questions for all types of theorems in Riemannian geometry. If you put some conditions and then if equality holds and you get your manifolds equal to somebody, then if you're close to the conditions that you had, then you should be close to the rigidity statement. So this is a typical thing in Riemannian geometry, but it's also can be motivated by the Bartnik mass minimization program. So here, one has a compact initial data set, say a compact Riemann 3 manifold with non-negative scalar curvature. It has a boundary. You look for asymptotically flat extensions of that with non-negative scalar curvature, and you try to find the one with the minimal mass. Okay. This is a way to define quasi-local mass. It's supposed to be a static vacuum extension with some agreement of the induced metric on the boundary and the mean curvatures, and whether or not this exists or not is a major open problem. So this type of stability question for the mass is like a test case, a very simple test case, whether or not you can apply maybe the direct methods in the calculus of variations to study Bartnik's mass minimization problem. Okay, so what is the conjecture made by Lee and Sormani in their initial study of this problem? So what they say is that, yes, these manifolds should converge to Euclidean space in a special sense called the volume-preserving intrinsic flat sense, assuming there are no interior compact minimal surfaces. Okay, so what we'll see is that horizons or minimal surfaces provide problems for us when we're trying to show convergence to Euclidean space. Okay, so the first question is why this notion of intrinsic flat convergence? Why is this important? So courtesy from the Lee and Sormani paper, I have this nice diagram which shows 4 sequences of asymptotically flat, non-negative scalar curvature manifolds. They're actually rotationally symmetric. And what you can see is that as the sequences progress, the masses get close to 0. They're getting more and more flat, so the mass goes to 0. But certain things are happening. For instance, this has a well. The well is getting smaller and smaller, and so it appears this is converging to Euclidean space. In fact, it converges smoothly, just by direct sight. Here, there's an actual minimal surface or boundary, but it's getting smaller as the mass goes, which you expect from the Penrose inequality. And this converges smoothly outside the origin but to Euclidean space, but also converges in the Gromov-Hausdorff sense to Euclidean space. In the next examples, again, you have the same phenomenon, except that you have a very long tube or cylinder-like extension, which can either get infinitely long or stay a fixed length long and will not converge, even in the Gromov-Hausdorff sense, to Euclidean space. Yet it will converge in the volume-preserving intrinsic flat sense to Euclidean space. And so that's the idea. We want to have a weaker notion of convergence with some compactness theorem, which was proven by Winger, that shows we can converge to the spaces that we expect. Okay, so that's the idea. So what is the definition of the intrinsic flat distance or convergence? Okay, so this is a very technical definition, which we will not delve into. I'm sure Christina will be glad to enlighten anyone about it. Ultimately, to state it precisely, you need to know what integral currents are, and you need to define them even in metric spaces. So you need the Ambrosio-Kerheim theory, which we will not need for our purposes, so we'll just avoid that and just give an intuitive sense of what this distance is. So we have two, say, Riemannian manifolds. Think of these as compact domains. You want to measure the distance between them, put them inside some metric space, or even just a Riemannian manifold, so you can compute distances and measure the filling distance, the filling volume between them, and try to make that filling volume as small as possible. Okay, so that's the idea. And so that's the intrinsic flat distance. And if you take the volume preserving intrinsic flat distance, you just add an extra term which says that the volumes will converge to each other if the limit goes to 0. Okay, so one thing you can do to get a sense of what's going on with this is to prove a necessary condition. So if you are converging in the volume preserving intrinsic flat sense to Euclidean space, then it was shown by Portuguese and Jarguy-Lee that the volumes of balls of fixed size are converging to that in Euclidean space. Okay, so intrinsic flat convergence is really associated with volumes. Okay, volumes converging instead of distances or derivatives in Sobolev norms or things like that. Okay, so it's a very weak form of convergence, which is sort of tailored to scalar curvature. Whereas Gromov-Hausdorff, you think of being tailored to Ricci curvature or works well with Ricci curvature bounds. This volume intrinsic flat is tailored to scalar curvature. Okay, so what are some problems that can occur? Why does this assumption of no horizons appear? Well, we can consider very simple examples. Take short-shelled manifold, the t equals 0 slice and extended short-shelled manifold. You have a minimal surface in the middle, and take the masses going to 0. Okay. So if you look at balls of fixed size centered at the center, centered at one point on the minimal surface, and as the masses go to 0, what you can see is that the shaded region is the ball of a fixed size, and what happens is this is converging to two copies of Euclidean space, but the shaded regions are converging to double the volume of the ball. So according to the previous theorem that we just cited, this cannot converge in the volume-preserving intrinsic flat sense to Euclidean space. In fact, in any reasonable notion of weak convergence, this is converging to two slices of Euclidean space. Okay, so this is not. So having a horizon here is a problem. Another one is you can have this bubbling effect. Here you take a short shield, attach it to the round sphere. Okay, so to make sure that the induced metric agrees with each other and that the mean curvature agrees with each other. Then that means that the scalar curvature across the gluing surface is non-negative in the distributional sense. Okay, so you can smooth this out in many ways. You can do Ricci flow. There's other techniques. You smooth it out to get a manifold non-negative scalar curvature. It's asymptotically flat, but as the mass goes to 0, you can see it's converging. And these balls, again, this is the shaded region of a ball of fixed radius. It's converging to a ball of fixed radius, that same radius inside Euclidean space, plus a ball that radius inside the sphere. So you're not having, again, volume preserving intrinsic flat. You're converging in any reasonable notion to a Euclidean space attached to a sphere. Okay. So this is what happens with, so we just eliminate that and say that we don't allow horizons except possibly the boundaries of these manifolds, the sequences. Okay. All right, so what is the precise conjecture? Okay. So here again, recall the actual rigidity statement for the Riemannian positive mass theorem. And the almost rigidity conjecture looks a little bit different. I have to explain some notation and what's involved here. But the idea is it's a type of pointed convergence. So you have this anchor surface. You think of this anchor surface of fixed area A sitting outside in the asymptotically flat end. So take a nearly round sphere and just fix the area in the entire sequence. You also fix a distance d that is bigger than the area radius if you were in Euclidean space for this area. So this would be the radius in Euclidean space for a sphere of this area. So you fix a distance, any distance d bigger than that. You fix these two things in the sequence. And for any choice of these two, the tubular neighborhood, so this is the tubular neighborhood of the anchor surfaces, And this is just saying you're inside instead of outside the tubular neighborhood. You're going inward instead of outward. This converges to a ball in Euclidean space in the intrinsic flat sense. Okay, so that's the idea. So you take an anchor surface, you take a tubular neighborhood, take the inside part of it. This omega just says you're taking the inside part of it. It's the region inside that anchor surface. And that's going to converge to the ball. Okay, so that's the idea. So this, right now it's a conjecture, but it was established in the case of spherical symmetry by Lee Sormani. It's been studied in other settings as well. So Huang, Lee, and Sormani studied this in the graphical case. So if you have graphs in Euclidean space, asymptotically flat, the conjecture holds there. Sormani and Stavrov studied this in the case of the geometric static setting. And there's related work by LeFloc, Sormani for H1 Lote convergence, Allen for foliations by inverse mean curvature flow, and Bryden in the axis symmetric setting. Okay. All right. So one question is, why these tubular neighborhoods? Well, the issue is that in these examples that we've discussed, you have these gravity wells. These can become infinitely long, and they can enclose infinitely large volumes. So this is very bad for intrinsic flat. We're just talking about convergence of volume. So this is going to happen. So you can't prevent this. So what you're going to have to do is restrict yourself to in a way that you don't go down to the bottom of the well. Okay. So we're fixing these tubular neighborhoods so that even though the well is getting very, very long, you're going to stay above this point here at the bottom. So this purple region, you're going to stay above. Okay, that's the bottom of the tubular neighborhood. So this guy may keep going longer and longer. The point is that the volume after that should get really, really small as long as you fix the distance down the gravity well that you're allowing yourself to go. So that's the reason why you take these tubular neighborhoods, so you don't go all the way down the well, and you can keep the volumes outside your tubular neighborhood small. Okay, so back to the space-time positive mass theorem. So this is the question that we're discussing in this talk. So there's an issue here as well. So suppose your masses are getting small. What does it even mean to have a rigidity statement where you're trying to embed in Minkowski space? Are you close? What does it mean to be close to embedding into Minkowski space? As I said, either you can get a sequence of embeddings and they converge to an actual something in some way in Minkowski space, or you can have embeddings into spacetimes which are close to Minkowski space, and those things are converging actually to Minkowski space. So that it turns out that we took the second approach because we couldn't figure out any way to deal with the first approach, and this is the reason why. So actually, this figure is a very good, this diagram is a very good one to understand. So we can take just graphs, take graphs in Minkowski space. They all have mass 0. I mean, make them asymptotic flat, they have mass 0. And moreover, the second fundamental form of the graph agrees with the second fundamental form of the data because it's actually a graph in Minkowski space. So now this is a natural test case where you just take graphs in Minkowski space. We have a sequence of initial data, and we try to find all the pathological behavior that such things can exhibit. Okay? So one of the pathological behaviors that it can exhibit is that these guys become very close to being null. Okay? They converge to a light cone. In fact, you can make them converge to a light cone. And there's nothing you can do about that. Okay? That just happens. But what's bad about that is that then volumes of balls on those regions, they go to 0. So we have large regions of the initial data where volumes are going to 0. And from the point of view of intrinsic flat convergence, this is not good, right? Because we want convergence of balls to something. So if it's all converging to 0, we couldn't figure out a way to deal with this situation. So the solution we came up with is that we're going to construct embeddings into spacetimes that are close to Minkowski and show that those spacetimes converge to Minkowski instead of trying to show the actual embeddings converge. In other words, instead of trying to show that the metrics G converge to something, which is the initial data, we're going to show that the spacetimes they embed to converge to Minkowski. We're going to find spacetimes, static spacetimes that they embed into, and those static spacetimes will converge to Minkowski. That's the idea. So here's the the conjecture. We do have this extra decay on the trace of the second fundamental form, again, because the Zhang equation will be involved, and we need to be able to have the barriers for that solution. So what we're saying here is, under the typical assumptions, now instead of no minimal surfaces, we're saying there's no compact apparent horizons, the analog of minimal surfaces, except possibly at the boundary of our initial data. Dominant energy condition is holding, asymptotically flat, the standard assumptions, and the mass is going to 0. So what is the conjecture? The conjecture says that these manifolds isometrically embed into a sequence of static spacetimes, okay? And this sequence of static spacetimes converges in the intrinsic flat sense to Minkowski space. Now, there's not actually a definition of a spacetime converging in the intrinsic flat sense, but what we mean by that is that the basis, the t equals 0 slice, converges to Euclidean space in the intrinsic flat sense. So again, the almost rigidity statement here is that we produce spacetimes that are close to Minkowski space. Our initial data embeds into those spacetimes, and then those spacetimes converge in the intrinsic flat sense to Minkowski space. That's the idea. Moreover, of course, the second fundamental forms should be getting close to each other, going to 0. And what we were able to, well, the conjecture is that under an additional assumption where there's a uniform bound on the second fundamental form in L2, okay, perhaps this can be removed. It's a technical assumption for us at this time, but we include it. The difference of the second fundamental forms on these tubular neighborhoods goes to 0, okay, in L2. So that's the analog that's the rigidity statement for the spacetime positive mass theorem. What we have found to be true in a certain situation, and we believe there's some reason to believe that it should be true in general. Now, just to recall why we make these certain assumptions, first of all, as I point out, because of the examples, the actual initial data may not converge in any nice sense whatsoever. So we just completely ignore what's happening to that and just talk about the spacetimes they embed into. We use volume and preserving intrinsic flat to deal with the wells, which Gromov-Hausdorff cannot deal with. No horizons means you eliminate this bubbling phenomenon, and the tubular neighborhoods keeps you from going all the way down the gravity wells. Okay. All right, so we were able to prove this in the spherically symmetric case, just like Lee and Sormani were able to do the Riemannian positive mass rigidity in the spherically symmetric case. So the only difference is that in the conjecture we had L2 convergence of the second fundamental forms. Here we replace that by LP for any p less than 2. This is perhaps a technical, I mean, for us it's technical. I believe it could be improved to L2, but at this time I'll explain why we can only get p less than 2, but it should be advanced to L2 in any event. That's what we have at this time. So let's review. What is a spherically symmetric initial data set? So the metric, so first of all, your manifold is diffeomorphic to Rn minus a ball or to Rn. It depends if you have a boundary or not. And your metric is determined by two functions. Actually, it can be determined by a single function if you take geometric coordinates, say the arc length parameter, then the first coordinate function is just 1. But here, r is just an arbitrary radial coordinate. Then you have these two. This is the area radius. And then the second fundamental form is also determined by two functions, kt and kn, the normal and tangential pieces. Okay. All right, so in order to describe the proof, we're going to prepare and describe some initial properties that such initial data have under the basic assumptions that we have made. So the first thing is to observe, I'm not sure if this has been observed before, but it's certainly something that is very useful, that the outermost apparent horizon, if you have any kind of symmetry, in particular spherical symmetry, the outermost apparent horizon, if it's smooth, is also going to be spherically symmetric. So I say if smooth because in high dimensions, right, you could have these possible codimension 7 singularities. So we want to avoid that issue. In low dimensions, they will be smooth. So this can hold for any type of continuous symmetry. Just if you have a killing field and say the outermost apparent horizon is not having that symmetry, so then that killing field at some point is not going to be tangent to the surface. So you can flow outward. It's going to stay an apparent horizon under that flow. But now there's a little piece that lies outside the original surface. But we know there is, according to basic existence theory, there is an outermost apparent horizon that must lie outside both of those surfaces. So in particular, it must lie outside the original one if you flow a little bit outward. And so therefore, you must be, you could not have been non-tangential. So any killing field that is a symmetry for the initial data will be tangential to the outermost apparent horizon. And this is the same thing for outermost minimal surfaces in the Riemannian setting. The second thing to observe is that this area radius function, because we're assuming there's no apparent horizons except at the boundary, this is always increasing. Okay? Once you start at the apparent horizon, it continuously moves upward. It can't go down or any other direction. So the reason for this is very simple in spherical symmetry. So this is the formula for the null expansions, the null mean curvatures. So we have the derivative of the area radius and also a piece, the tangential piece of the second fundamental form. If you add them together, you get just the derivative of the area radius. And this must be positive because we're assuming there's no other apparent horizons. In other words, these two null expansions must be both positive outside the apparent horizon boundary. Okay, okay, the next last piece of preparatory information for these type of initial data is the Penrose inequality, which holds in full generality for all dimensions here. So you can bound the mass below by the area of the apparent horizon if it's an outermost apparent horizon. If equality holds, then you must arise from an embedding into short-shilled spacetime. Okay. So what we use this for is to show that the area of the boundaries must go to 0 if the mass is going to 0. Okay. So what's the proof? Okay. So in general, this, I believe this is a new result. It's not too hard to prove, but it comes from an observation that I don't think is well known. But if you consider the generalization of the space-time Hawking mass, okay, so if you replace the product of the null expansions here with just the mean curvature squared, this is just the standard Hawking mass, which works well in the Riemannian setting under inverse mean curvature flow and so forth in 3 dimensions. But in general, this is what it looks like, and it turns out under the assumption, the dominant energy condition and spherical symmetry, where you can think of the foliation by coordinate spheres as a smooth inverse mean curvature flow, this is monotonic. It agrees with what you want on the apparent horizon boundary, okay, because one of the null expansions vanishes there. At infinity, it converges to the ADM mass. Okay.
I'm pretty sure the proof is in the literature.
Okay, so I went through the literature, and so in 3 dimensions, Sean Hayward has done this, and then there are some. I mean, I don't know.
Is it a survey paper by Mars?
Mars has a survey paper. I'm not sure he does all dimensions. And moreover, every place that I've seen this written does not address the case of equality, that you get an embedding into short-shilled. Okay. Anyway, there's ways that you can prove this. The way I prove it is with a generalized version of the Jang equation. It's very simple that if you take this, we'll take Jang deformation and take the regular Hawking mass in the Jang deformation, it basically is equivalent to this mass in the original initial data. And you can show that the Hawking mass in the Jang deformation is monotonic, and so therefore this one is monotonic. Anyway, the nice thing about that approach is that it gives you very nicely the embedding in the short-shilled. The Jang graph will be the embedding in the short-shilled. Anyway, we will use this result. Okay, so the first deformation, so we will follow the approach of Shane Yao in the positive mass theory. We have 2 deformations. One is the Jang deformation. So let's motivate this a little bit. Okay, so you can, let's take a graph in Minkowski space, and we take an initial data set, MGK. one question you can ask is, does this initial data set arise, does it arise from Minkowski? If you're given initial data, it's not that easy to determine if it arises from Minkowski space, okay? But one way to do it is to form this, these two quantities, a g-bar metric, the Jang metric, and also this k-bar, which is a difference of second fundamental forms. Your initial data arises from Minkowski space if and only if k-bar is 0 and g-bar is Euclidean. Okay, so that's one way to view it. So a necessary condition is to take the trace of k-bar with respect to g-bar and set it equal to 0. That's a necessary condition to be embedded into Euclidean space. And so that's exactly the Jang equation. So one way to view the Jang equation is, because we can take initial data and solve the Jang equation, whether or not it's embedded in Minkowski space or not, you get some solution. And then you can view the Jang graph as if there was, what do I say, as an attempt to find a candidate graph for an embedding into Minkowski space. Okay, so that's one way to view it. Okay, so what do we use this for? So in our setting, we're trying to construct static spacetimes where our initial data embed into, and then those static spacetimes converge to Minkowski space. So the Jang graph will be the embedding, and it will also give rise to the static spacetime. So the idea is take the Jang metric, so you solve for f, and remember g bar is g plus df squared. You can take that as your t equals 0 slice of some static spacetime. Just construct such a static spacetime, and then automatically, just by the way the Jang graph is set up, this is an isometric embedding of the original initial data into the static spacetime. Okay, so these will be the candidate spacetimes where initial data live, and here's the formula for the second fundamental forms. It's important to understand what the geometry of these things look like, okay? Because there's two dual settings for the Jang graph. So the light blue is the original initial data, which has a horizon boundary, and then the Jang graph tends to blow up at apparent horizons, and typically, and you can make this happen as I'll discuss, has a cylindrical end. It blows up in a cylindrical fashion over the apparent horizon. Now, what we want is a graph over the Jang deformation. So you view this purple object as the t equals 0 slice of your static spacetime, but it's a little bit strange because you have this cylindrical end at the interior piece. And the effect that has is that when you look at the Jang graph, and the induced metric is exactly the original induced metric, it's a cylindrical end, but it has a finite boundary. And the reason why that is happening in the static spacetime is because this is becoming asymptotically null. Okay, so that's the dual setting. Well, it depends which one you call the original, but that what I'm going to discuss now is the original setting, the setting or way to view the Jang deformation from the point of view of what Shin and Yao did, and that is to view the Jang graph not embedded into a space-time with Lorentzian signature, but into Riemannian product, the same thing except that you have the original initial data as your base, t equals 0 slice. Okay. So in that situation, when the Jang graph blows up, you actually have cylindrical ends. They're infinitely long because you're in a Riemannian product instead of a space-time. So what is the point of that? And the Jang equation is geometric. It's just the apparent horizon equation in this one higher dimension. And the point is that the scalar curvature of your initial data, which is not necessarily non-negative, inherits some non-negativity property in the form of this formula. So if you look at the formula for the scalar curvature of the Jang deformation, if the dominant energy condition holds, this is non-negative, so W is some vector that has norm less than 1. These two are squared, and the only thing that could possibly cause problem is this divergence term, so we could perhaps say that the scalar curvature is weakly non-negative, or non-negative up to a divergence term. And so in the proof of the positive mass theorem, this allows a conformal deformation to 0 scalar curvature because you've gained enough positivity for the scalar curvature. And then the mass of the conformal deformation is lower than the mass of your original. And then you just apply the original time symmetric version of the positive mass theorem. Okay, so we will actually require blow-up solutions. So what we were doing, we need the blow-up solutions if we have the horizon boundary. And in dimension 3, one can actually, this has been studied, one can prescribe blow-up at the outermost apparent horizon. And this is fine in higher dimensions. One has potential difficulties because, again, the singularity theory for Zhang's equation mirrors that of minimal surfaces. However, in spherical symmetry, it's very nice. One can do this in all dimensions without any difficulty. The reason why is because Zhang's equation actually reduces to a nice first-order ODE by defining this quantity, which already involves one derivative of f. And what's nice about this ODE is that the apparent horizon or null expansion appears almost explicitly in the equation. So this term here, if v is equal to 1, this is theta minus. Okay, this is so the null expansion appears there. So the blow-up occurs precisely when v is plus or minus 1. You either blow up or blow down. And so if v is plus or minus 1, you get, in this slot, either one of the null expansions. And from this, you can do simple maximum type principal arguments to show that you get uniform C0 bounds, where this object, this v, can never touch 1 or minus 1 away from the initial surface. Okay? And once you get this, then you can just bootstrap and solve this equation. So in other words, we can prescribe that v is equal to plus 1 if you are a future apparent horizon, or minus 1 if you're a past apparent horizon, and then just solve and get a solution to Zhang's equation. So we get these blow-up solutions very easily in spherical symmetry. We can prescribe it. If you just have a complete initial data, then you can solve Zhang's equation, but you don't know where it's going to blow up. You don't even know if it's going to blow up. If it blows up at apparent horizons, but you don't know when or which apparent horizons it will blow up. Okay, so we have this Zhang deformation. We would like to go to scalar curvature, just like Shen Yao. So the point is, from the formula of the scalar curvature, one can multiply by test function and integrate by parts to arrive at this stability type inequality. Okay. And the point is that on the left-hand side, this is the energy associated with the conformal Laplacian. It's actually the Yamabe functional minus the denominator term. And so what it's saying is that the spectrum for this operator is positive. And so therefore, we can solve on compact sets the Dirichlet problem and then take exhaustions and get a solution, which goes to 1 at infinity and is bounded as you go down the cylinder. In fact, as you go down the cylinder, it will be forced to go to 0. But I just want to point out that it appears that it's not negative only the spectrum here. But if the spectrum is 0, then all these individual terms have to vanish. And that would then imply that the scalar curvature of the Zhang graph vanishes, which means you're reduced to the Laplace equation. And the Laplace equation has strictly positive spectrum. OK. So just to record what we have the first deformation to Zhang, then the second deformation to 0 scalar curvature, and the relation between the masses of the two deformations is of this form, where alpha is the monopole at infinity. Now, when you're going along the cylinder, the conformal factor goes to 0 exponentially fast. So you conformally close these ends. In the proof of the positive mass theorem, a preliminary deformation to achieve strictly positive dominant energy condition was needed to achieve this. But in our setting in spherical symmetry, it's automatic because our surfaces are round spheres. Okay, so the spectrum for this operator is strictly positive. Okay, so there's a very dramatic rigidity that happens when you're in spherical symmetry and you follow this outline. And that is, after conformally transforming to 0 scalar curvature, there's only one thing that you can be, and that's Euclidean space. Okay, so this follows from a well-known lemma, which was apparently we had difficulty finding a proof of it in the literature. I mean, it's not very difficult to prove, but if you're spherically symmetric, you're complete and you have 0 scalar curvature, then you're either Schwarzschild or you're Euclidean space. Okay? So for us, when we conformally go to 0 scalar curvature, because the cylindrical ends are being conformally closed, we can compute that the mass is, or the Hawking mass is 0, and the Hawking mass is determined which one of these things you are. And so the only thing that our solutions can be is Euclidean space. So at the end, if we go through the deformation process, here's the Jang, then the conformal change to zero scalar curvature, you must be Euclidean. So the Jang metric, which is again the base of the static spacetime, is conformally related to the Euclidean metric. It's conformally flat. I mean, another way to view that is, which is not, you can avoid this theorem, is to note that all spherically symmetric metrics are conformally flat. Okay, but then you need to analyze possible conical singularities at the origin and so forth. So what that says to us is that what we really need to focus on is control, uniform control on U. Okay, so here's where the start of the uniform control on U comes from. So because the mass of the conformal change is 0, then the mass of the Jang metric, which is the same as the mass of the original, is just minus 2 of the monopole. And so when you go back, multiply the scalar curvature equation by U and integrate by parts, you get this gradient L2 bound for the conformal factor. And it's telling you that it's going to 0 whenever the mass is going to 0. Because it's conformal to Euclidean space, we can immediately get that when you go to the Euclidean setting, we have gradient L2 bounds for log U instead. But now it's log U on Euclidean space. Okay, so but for the volume preserving intrinsic flat convergence, H1 bounds are not enough. What we need is something more along C0 bounds. And so we can do this. So what we assume is that the sequence of manifolds that we're dealing with are uniformly asymptotically flat. Okay, so it just means that they all have the same, when you define asymptotically flat, the constants and the radius of the ball out which in Euclidean space that the diffeomorphism occurs, they're all uniform. With that and the uniform gradient L2 bound, we can integrate in from infinity and get a Holder bound, okay, on the log up to any finite distance. Okay, so we take a large sphere at infinity, integrate inward to any finite distance, and we get C0 1/2. I mean, the reason why it's C0 1/2 is because the solar space W12 embeds into C0 1/2 for dimension 1. Okay, that's why we get C0 1/2. And so this is going to 0. As long as you just fix a cutoff, you don't go all the way in. Okay, so now we're able to start the intrinsic flat convergence. So the first thing to observe is that the volumes of the two sets, one in Euclidean space, one inside the Jang metric, will converge. So what we're going to do is break it up into two regions. One is a large region starting from the anchor surface in the asymptotically flat end, going to a small cutoff surface where inside this region, this annular region, which is the red region, we have uniform control on U in C0. Okay? And the remaining piece, the dark blue, is going down the cylinder. This is supposed to have very small area cross sections. And so then the volumes, if you fix your tubular neighborhood's diameter, then those volumes should be going to 0. In fact, so from the co-area formula, and so the fact that the area radii are always increasing, we can estimate the volume inside this, this dark blue piece by the area of the top slide, the top cross section, and then the diameter, so d times a epsilon. A epsilon, again, is very small. By the Penrose inequality, mass goes to 0. These cylinder cross sections have to go to 0, and so this is very small. So for the remaining regions, we have uniform control on U. It's close to 1. And so you're uniformly close to the Euclidean metric, and so therefore these regions get close to the volume of the Euclidean ball. Okay, and so therefore we have this convergence to the Euclidean ball. So the volumes get close. Okay, so there's a very helpful theorem, the Laxian-Sormani theorem. If you want to estimate the intrinsic flat distance, you can use this as a basic model. Okay, so what it says is if you have two two manifolds. You want to show that they're close in the intrinsic flat distance. Find diffeomorphic subregions which are uniformly close to each other in C0. And so for us, that will be outside, in the annular region, outside the small radius cutoff surface to the anchor surface, where we have uniform control. And then bound all the volumes and all the diameter volumes of the boundaries and of those regions. And then show that what's left over, the parts that are down, for us, down the cylinder, those are a small volume. Okay? And lastly, that the distances in those uniform regions can be compared and be very close together. Okay. So let me show, there's a better way to see this in a picture in the next slide. So here's the Jang metric. Here is the Euclidean metric. We're trying to show these are close to each other. So we have this large anchor surface in the asymptotically flat end in both settings. They have the same area. And then we have a cutoff surface, A epsilon, down here. And in here in Euclidean space is this little guy. So what we want to do is show that the volumes of these leftover pieces, so this is the A epsilon cutoff surface. The volume after that is very small because the cross sections are going to 0 and your tubular neighborhood's diameter is fixed. And the same thing for this dark purple region. Those are going to 0. And that's exactly what these statements say. Again, it's the same idea with the co-area formula. In the light blue pieces, that's where we have uniform control of these. The U is close to 1 in C0. And so therefore, those two, everything will be very close. And so it satisfies the assumption of the Laxian-Sormani theorem. This is just another illustration of why that theorem works. So remember, the intrinsic flat distance is, like Gromov-Hausdorff, you want to embed with distance-preserving maps into a metric space, but instead of comparing tubular neighborhoods, as with Gromov-Hausdorff, you compare filling volumes. So this is actually a caricature of the filling volume between the two embedded into some metric space. Actually, these things were constructed explicitly by Laxian and Sormani. And so this parameter lambda j, which measures the difference between the two distances, those things are related to the height of this of the embedding between these two objects. Okay. So to show, the last thing you have to show is that these two are small. That these two distances are very close, one in the Jang and one in the Euclidean space. So the reason why they're very close to each other is, first of all, these 2 points are always inside the place where you're uniformly close to Euclidean space because we have the C0 control there. And that's why we have this d epsilon. That's what this says. That's the difference between the uniform control. But the problem is that geodesic connecting the two can go down into the cylindrical region where we don't have C0 control. However, we can take a shortcut, or not a shortcut, but a different path, which we can show is already small. So for instance, once you pass that very small sphere, you can take the great circle on that small sphere, so just going from here to here. And that distance is just pi times the area radius of that very small radius sphere. And so then that's also going to be small. So that's the only leftover piece when you compare these two distances. And so therefore, they will be small. And we get the intrinsic flat distances go to 0. So the only thing left to talk about is the difference of second fundamental forms. So we've shown that we can isometrically embed to these static spacetimes. The bases of these static spacetimes converge in the intrinsic flat sense to Euclidean space. But in order to be an appropriate rigidity statement for a positive mass theorem, the second fundamental forms of these embeddings must get close to the original second fundamental forms in some sense. Okay, so again, here we have to deal with the inside and the outside, the place where there's small volume and then the place where we have uniform C0 control. So from the stability inequality, from the non-negative property of the Jang scalar curvature, we get this immediate inequality. So the mass bounds the difference of the second fundamental forms, but there's this presence of the conformal factor u. The problem is u goes to 0 down the cylinder, so we can't go all the way down, even though it looks, this is actually this is a global integral. It goes all the way down the cylinder, but we want just the L2 bound of the difference here. We don't want to have u because u is going to 0. If we restrict to everything outside a small cross section here with the a epsilon, where we take everything outside, then u is close to 1 on that region, and so we can say it's u squared is bigger than or equal to 1/2, and we get the bound immediately. So outside control follows immediately from the stability inequality and the control, uniform control on u. Okay, so inside down the gravity well, we were not able to show that the L2 norms go to 0, but what we were able to show is that the L2 norms are uniformly bounded. So again, this is on the tubular, this is actually globally, not just down, but on the full tubular neighborhood, there's a uniform bound in L2 for these differences, and that is assuming this uniform bound on the second fundamental forms, the L2 bound. So the way one achieves that is, again, from the stability inequality. Remember, you can plug in any test function you want. If you plug in appropriate test functions, this object appears. And if this is uniformly controlled, then it's not too hard to arrive at control of this. So the last thing to explain the reason why we have p less than 2, any p less than 2, well, we just use Holder's inequality. On this small region below the cutoff surface of area A epsilon, the volumes are small, and so by using Holder's inequality, we can get LP tending to 0 because the volumes are small. Now, just to say that there's no way to improve this going all the way down, because as you blow up, as the Jang equation blows up into the cylinder, as you go up, h minus k converges actually. If you forget the sequence, just take a blow-up of the Jang equation. This h, which is the second fundamental form of the graph in the spacetime or in the Riemannian product, this converges to the second fundamental form of the boundary in your initial data, and then this converges to the restriction of your k onto the boundary of your initial data. And there's no reason, I mean, you can construct examples where those two do not agree, and therefore, actually, h minus k is not even in L2 if you just take a fixed blow-up solution of the Jang equation. So you have to do something where you use a tubular neighborhood or do some other restriction to keep from going all the way down the cylinder. Okay, that's it.